Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module etching techniques from the paper Semiconductor Materials and Devices. So students, now let us see what we are going to learn in this module. We'll study about the bulk and surface micromachining, wet and plasma etching techniques, and detailed descriptions of reactive ion etching technique and dry reactive ion etching technique. So etching is a process used extensively in the microfabrication process. Etching process include all the techniques which are aimed at uniform removal of material from the surface of a wafer. It is mostly used in parallel with the process and is used to cut open the protective film on the surface. These openings are further explored to develop semiconductor region by means of diffusion and implantation. Etching can also be used to delineate metallized layers. Chemical matching of a semiconductor is incorporated into fabrication process by the process of etching. Microelectromechanical system MEMS devices have very small size, mass and volume with low cost of production and low power consumption. They can be easily integrated into systems and can be fabricated into large arrays. They find application in various aspects of day-to-day life and also at industrial scale such as in the shock and tilt sensing, surface shutoff, STMs and many more. Bulk micromachining as well as surface micromachining is used to develop microstructures onto the surface of these MEMS devices. Bulk micromachining mostly utilizes wet etching techniques for the purpose of fabricating microstructures, whereas surface micromachining uses dry etching technique. As the name signifies, bulk etching focuses on removal of bulk material from a substrate. In bulk micromachining, silicon substrate is selectively etched, creating cavities and hence forming microstructures. A silicon dioxide, that is SiO2 layer, is deposited first over silicon to protect certain areas from etching. This is done mostly by thermal evaporation technique. Then windows are opened on this SiO2 layer to pave the path for etching as shown in the figure. As the name suggests, wet etching involves the use of aqueous chemicals which then etch the wafer surface away. Chemicals like potassium hydroxide, TMAH, hydrazine water are used for the purpose of wet etching. These etchants are isotropic in nature, that is, silicon is etched equally in all directions, whereas when this etching takes place uniformly in only one direction, that is vertical direction, it is termed as anisotropic etching. This etching process takes place along a certain plane of the substrate and etch rate is different along different planes. On the other hand, surface micromachining involves the deposition of a pattern layer and then sacrificing the same layer eventually. Micromechanical systems are created by deposition and etching of these thin structural films. Using surface micromachining, simple as well as complex structures can be fabricated on the substrate. When silicon is used as a substrate, then mostly silicon dioxide is used as the sacrificial layer, while polysilicon is used as the material for microstructures. Very small microstructures which can be fabricated using surface micromachining. This is a big advantage of surface micromachining. Also, it allows integrating of microstructures with microelectronics on the same chip along with low cost and mass production advantages. Now let us study some points about wet etching. Wet etching can be done by various methods and is dependent on parameters of thin film, porosity of film, process of film formation, or the various processes it has been subject to before etching. While etching, a few things should be kept in mind, like chemicals which are used to dissolve materials in bulk form are commonly used for thin film etching also, but the film material will suffer a faster rate of etching as compared to bulk material. In order to avoid over-etching, the chemical must be used in dilute form. Diluted chemicals reduces the etch rate to a desirable state. Thin film which are grown by E-beam evaporation or have been subjected to E-beam in any of the previous stages or the ion implanted thin film are characterized as irradiated films. We should remember that irradiated films will etch rapidly in comparison to non-irradiated film. Though using a negative resist can help us as these resists get toughened due to polymerization induced by the irradiation. Substrate temperature, change in temperature of surroundings and rate and manner of film deposition influences the amount of stress that develops on the thin film. This stress alters the rate of etching and it increases for high stress. Rapid etching can also be seen in films that have poor microstructures, which can be because of loose structures or high porosity of the film. If the preparation techniques of a compound lead to departure from its stoichiometry, then films of such compounds will have a high etch rate. Films which have a single phase will show a higher etch rate in comparison to multi-phase films, as preferential etching of one component rapidly increases the porosity of film and hence lead to higher etch rate. So students, now let us study about the plasma etching. Physical bombardment of ions or atoms on a substrate leads to removal of material. This etching is assisted by a gas discharge. It imparts energy to ions. Projectiles of these ions impinge on the substrate with high velocity and transfer their momentum to substrate atoms via elastic interactions. Plasma-assisted etching has been rapidly used in recent years. Despite of high cost of initial installments, this technique has flourished due to the following reasons. Etch directionally can be achieved without dependence on crystal orientation. The pattern formed by the process of lithography can be transferred faithfully, and it is comparatively clean method and compatible with vacuum processing techniques. The plasma-based dry etching techniques are able to achieve etch directionally due to the occurrence of a film forming process on the side walls of the features which are undergoing etching. These films are given the name of passivation layers. The passivation layers shields the side walls and stop the etchant species from attacking the side walls. This prevents mask undercutting. It is also comprehensively preventing any damage to side walls from off-normal ion bombardment. This reduces the bowing effect. But how are these layers generated? Energy and chemistry of glowing discharge, the type of substrate used, temperature of substrate, and the material used for the purpose of masking all play an important role in the formation of these layers. But details for their formation are still up for discussion. A right combination of these factors leads to deposition of this passivation layer on the features being shaped. The thickness of these layers can vary from 0.1 micron to few microns. Reactive ion etching. Reactive ion etching belongs to the class of dry etching techniques and uses chemically reactive plasma for the purpose of etching. It is accomplished by replacing the neutral species used for the purpose of etching in the process like sputtering technique or by chemical species. Ionized and neutral species are created by the interaction of these chemicals with plasma. These highly energetic species are used for the purpose of etching. Students, you can see figure shown on the screen, which is a planar reactor configuration used for the reactive ion etching technique. The substrate is immersed in plasma and the gas flow is kept normal to the substrate position. This setup allows the energetic species with small lifetime to be used effectively. This setup also helps in achieving high anisotropic etching as energetic species are highly directional. This directionality is due to the fact that substrate is kept normal to the RF field. This anisotropic nature of reactive ion etching can be enhanced further and is controlled by various factors. These factors can be altered or varied to yield better results, like we can use chemicals which will give products with very large number of ionized components, an increase in the voltage drop across the cathode sheath. This significantly increases the velocity of species responsible for etching. The system can be operated at a reduced value of pressure. By doing so, we can minimize the collision in the sheet and improve the directionality. Etch rate is also dependent on the area of the wafer, or rather the area of the surface that is to be etched. As this area decreases, the rate increases, and hence the etch time has to be reduced. This loading effect can be calculated by making some simple assumptions. Let us assume that the plasma produces a large reactive species with G as the generation rate per unit volume per unit time, and the recombination rate is given by tau. Also, for a given wafer temperature, K is the constant for the linear reaction where a single product is formed. Now, if N is the concentration of the reactant species, A is the area, and J is the flux density, then the flux density of the species and flux will be J into A is equals to K into A into N. If V is the volume of the plasma, then from consideration of continuity, dN by dt equals to G minus KNA by V minus N by tau. But for steady state, dN by dt is equals to 0. So, G minus KNA by V minus N naught by tau is equals to 0, and here N naught is the concentration of active species at a steady state. If R is the H rate, then it will be given by J by N, where N is the number of atoms per unit volume of the wafer. So we have R equals to G by N into tau K divided by 1 plus tau Ka by V. So from here we can infer that for tau Ka by V, which is far less than 1, the value of H rate R will be dependent of the area, whereas for tau Ka by V greater than 1, it increases with a decrease in A. A change in H rate may lead to complications in patterning fine lines. For tau Ka by V greater than 1, as the film clears, the H rate increases and leads to undercutting at accelerated rates. This can lead to loss of anisotropy. Hence, it is advised to load the reactor very lightly. This can be done by increasing the inter-electrode spacing. By doing so, we can increase the plasma volume and reduce the surface area, but the through output decreases, so it is rather better to perform single wafer processing. Two processes, that is, physical and chemical process, happen simultaneously in reactive ion etching. Both of them are responsible for the completion of etching process. The physical process is based on sputter removal technique. This ion bombardment process, the rate of etching is dependent on the sputtering yield. It shows poor selectivity. The chemical process is highly isotropic in nature. The energetic chemical species that participate in etching are selective and specific towards the material it can etch. Keeping a balance between these two processes is essential for successful etching. This balance can be achieved by controlling the parameters such as RF voltage, substrate self-bias, chemical species, etc. As mentioned earlier, the formation of a passivation layer during etching is very advantageous. The ion beam, which is highly directional, remove these layers of native oxides and polymeric products normal to the surface. Also, due to the directionality of this beam, The side walls are not attacked and hence remain unetched. Due to this, undercutting of grooves is prevented. The iron beam also increases desorption of the etching products. These etching products are adsorbed and removed by using a pumping system. Endpoint detection schemes are a major part of reactive ion etching. Such schemes are needed because it is difficult to predict the extent of etching. So now students, let us study about the dry reactive ion etching. Etching refers to the chemical removal of layers from the surface of a wafer or substrate to create cavities which can be filled with desired materials, hence developing the micro devices. One of the methods to achieve etching is dry reactive ion etching. Dry reactive ion etching or DRIE makes use of the chemical reactive plasma to remove materials deposited on the surface. This gaseous form of etching is mainly used for obtaining highly anisotropic etching, a disadvantage of the wet etching process. A typical parallel plate RI system is made of a cylindrical vacuum chamber with an electrically isolated wafer platter that is situated in the bottom of the chamber. Gas is made to enter through the small inlets present at the top of the chamber and exit to the vacuum pump system through the bottom. The types and the amount of gas used depends upon the etching process. For example, sulfur hexafluoride is commonly used for etching silicon. Gas pressure ranging between millitorr to a few hundred millitorr by adjusting gas flow rates. Plasma is formed in the chamber by applying a strong radio frequency electromagnetic field to the wafer platter. The oscillating electric field ionizes the gas molecules by stripping them of electrons, creating plasma. The electrons so formed are electrically accelerated up and down in the chamber, striking both the upper wall of the chamber and the wafer platter. The ions, however, being heavy, move relatively little in response to the RF field. The electrons striking the walls are simply grounded, but those deposited on the wafer platter cause charge buildup on the electrically isolated wafer. This negative voltage attracts the positively charged ions which accelerate towards the surface. The ions collide with the surface to be etched, both chemically reacting as well as removing the materials from the surface by shear momentum transfer. As most of the ions reach the surface vertically, very anisotropic etch profiles can be produced using this method, unlike the typical isotropic profiles from wet chemical etching. This highly directionality can also be achieved by varying parameters such as pressure, gas flows, and RF power according to our requirements. Boss technique. Even deeper trenches and penetrations with higher aspect ratio on the surface than those obtained from above method can be achieved by using deep reactive ion etching, also known as Bosch etching. This process can fabricate almost vertical but slightly tapered walls. The process is similar to dry reactive ion etching except alternates between a polymer like C4F8 and a normal plasma gas etching as achieved through dry reactive ion etching. The polymer forms a passivated layer like that of Teflon on the surface, preventing it from etching. However, during the collision of directional ions with the surface, the ions scrape off the polymer from the surface but not from the sides, exposing the surface to etching. Apart from manufacturing MEMS devices, this process is also extravagantly used to excavate trenches for high-density capacitors for DRAM and also creating through silicon vias in advanced 3D wafer level packaging technology. So students, let us summarize what we have learnt in this module. We studied about the bulk and surface micromachining techniques for etching. We also discussed two types of etching, that is wet etching and plasma etching. We also studied about the detailed description of reactive ion etching and the dry reactive ion etching. Thank you.